We started. Oh, man. I just want to go to bed. Sorry. Okay. And this is my long day. So we'll go from current slide, but let me, I went to put your present, but I forgot to, so do it now. There are announcements, and I don't think you'll be concerned with any one of them, but I'll do it for Corey's and Josh's benefit. This week, and it depends on how they define a week, the various schools, several of the schools in Alabama, well, I'll phrase it this way, the way it's said. Alabama State Department of Education teams up with the Alabama Possible to host college application. Some of this is cut off. So high school seniors in Alabama can apply to colleges and universities across the state for free for this week. Okay. Not all of them, and not for as long a week as some of them. Okay. Alabama is home to blah, 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 blah. This, oh, by the way, is from Doug Jones, our senator. So application week is what it's called. Provided, and here's something Doug Jones said. I also want to remind you that the two-year colleges are free to apply all year. Okay, there's no, I don't think ever an application fee for the state two-year schools. So anyway, he has other information. Here are the colleges where you can apply this week for free. Alabama A&M, Alabama State, Auburn, Auburn University at Montgomery, Fortis College, I'm not even sure where that one is, Huntington College, Jacksonville State University, Jefferson College, Marion Military Institute, Miles College, Selma University, I didn't even know that there was one, Spring Hill College, Stillman College, Talladega College, University of Alabama. They don't say UAB, which I was sort of surprised at, or UAH. Troy University, Tuskegee University, and then is there a University of Mobile? There's an MO, but it's cut off and I can't see the rest of it.
I don't think so. South Alabama was going to be.
Yeah, and well, they also list that, so I don't know what that one is. University of Montevallo, it's not that one, but there's another University of MO something. University of South Alabama, University of West Alabama. And he said, if you have any questions, please do not hesitate to contact him or his team. I really like that, Jones. Okay. And this is also sent by Miss Akili M. Haley, who is our career and college transfer coordinator. She has an office on this campus and the Birmingham campus. I didn't see her in today, but I've seen her in other days. Then, with that, Jacksonville State University sent their own. They said they're proud to participate in Alabama's College Application Week by waiving their $35 application fee November 4th through the 8th. So that was this week, and that goes till, is it tomorrow? I believe so.
It's Friday.
Friday, you're right. Tomorrow through Friday, okay. I mean, 4th through the 8th, okay. And so if you have more information, want more information about Jacksonville State, it's there. And then also we got one from the University of Alabama about it. And theirs goes 4th through the 10th. So they go through the full week. The other was a 5-day week. This is a 7-day week. So that's why I said some schools do different. So anyway, up till 11:59 p.m. Central Time on November 10th. Okay, so Sunday night at 11:59, you can still do it there. So anyway, there probably are another announcements out there. I just didn't have a chance to pull off any more this morning. I had several things going on. All right, any questions, anything we've done up till now? Okay, we're on in chapter 13, functions of several variables, 13.8, extrema of functions of two variables, and we were on page 942, example 2. Now, example 1 we did. Example 2 is not on the PowerPoint, so we're going to do this on the same page that we were on before, but we'll just do it on the screen down here. Determine the relative extrema of f of xy is equal to 1 minus x squared plus y squared to the 1/3. Sorry. All right. Now, all right. So, what would be your first step to do?
Find the gradient with respect to x and y, or gradient of x.
Okay, partial of f with respect to x. All right. Okay. And, ooh, goodness gracious. What would that give me?
That's minus 1/3 2x over minus x squared plus y squared to the 2/3.
Okay. All right, let's get Josh here. Did you know this week is the college application free week for many schools? Were you interested in applying anywhere this week?
No.
Okay, I was going to say, there are some schools here. I'll let you see the list if you're interested. Now, I wrote mine really dumb here, but it's all in here. Let me see if I can clean that up just a little bit. Back. Can't get the eraser to come up. There it goes. Okay. So what I'm going to do here is put the 2x with the 1/3 and keep the 3 with the other thing. Yeah, it's going to be ugly no matter what I do. Okay. Okay. Something like that. Okay. Now, and let's do the f's of y while we're here. Going to be very similar, right?
Except for the numerator, 2y.
2y.
Denominator, I have 3 times x squared plus y squared. Minus 2/3.
To the 2/3 again. So everything's the same except for the y in the numerator. Okay? Now, here's the kind of an issue here. Okay, remember and what we're looking for, the relative extrema, relative max or min. They're only going to occur where the partials are 0 or don't exist, right? Now this one will be 0, x equals 0, okay? This one would be 0 and y is equal to 0. Now, if both of those are equal to 0, then neither of these don't exist. So it would look as if your partial with respect to x, where x is 0, that would be the y-axis, okay? So you probably have a ridge there where your first derivative is equal to 0. You'd have a ridge also where along the x-axis where f of y is equal to 0, y is equal to 0. somewhat. But at the origin, nothing, it doesn't, the first derivative doesn't exist for either one of these, okay? So the place of most interest then would be the origin, where it doesn't exist, okay? And sure enough, that is your both partials exist for all points in the xy plane except for the 0, 0, and because the partial derivative cannot both be 0 unless both x and y are 0, then you can conclude it's the only critical point. Now, they didn't define what critical point it is, but if you look at this, the first partial is negative, okay? Second partial is negative, so the indication is, or at least sort of the gut feeling would be that this would be extreme max, relative maximum. Let's see if that would be hold out here. Your well, let's look here. Yeah, that would be the place to look at the actual function value. Okay, where this is 0, it's defined here. It has a value 1. The derivatives don't have a value, but the function does. Okay, and anything beyond x, y, anything, then it's decreasing. Okay, it could be decreasing big time. Okay, of course it's to the 1/3 power. That is, so this has to be a relative maximum. Okay, the reason these don't exist there is because this forms a cusp at the origin. They're coming up with different slopes from either side. So, indeed, and the picture's in the book, and that's indeed what you have. So it's a relative maximum at 0, 0. Sorry, I was telling Bill I've come down with a scratchy throat and a runny nose and a little bit of a cough, so not doing well. Okay. Any questions on that? Pretty kind of straightforward type analysis here. I keep wanting to move on because the next thing really is going to tell us more information than what we've been doing. And that's all example 1. I've got to sneeze, sorry. All I've got, okay, sorry. Sorry. When I get a cold, I get so temperature sensitive. Just a little bit of a chill and it just sends me nuts. My hands are cold for some reason. I touch something and that just made me want to sneeze. I'll try to make it. Okay, so the next topic is the second partials test. We've done the first partial derivative, and that tells us where we have relative extreme of possibilities anyway. Second partial test tells you a little bit more to find. That's why I had to stop before we did that one, so how far have we done here or not? To find the relative extrema, you need only examine the values f of x, y at the critical points. Basically what we did, went back to the function at the possible critical point. However, as is true for a function of one variable, the critical points of a function of two variables do not always yield relative maximum. Sorry. Let's go back to one variable, single variable calculus. When your first derivative is decreasing, you feel like there's probably going to be a max coming up. But as some functions then continue to go like this. So you do have first derivative equals 0, but neither a max nor a min. Cubic function is a great example of that. Sorry. There are other times where you can have, it not existing, and then moving. Okay? So, again, it doesn't exist there, vertical tangent line, but then it continues like this. What we just had, that did have a relative maximum, where the first derivative doesn't exist. Well, same thing here. Okay? When you have two variables going on, you could have a relative minimum in this direction, but a relative maximum in the other. And some of these critical points yield what we call saddle points. And we talked about this with our hyperbolic paraboloids. They usually do yield saddle points. Neither relative max nor a relative min. In one dimension, they look like they're going to be a relative maximum, but in another dimension, they're going to look like relative minimum. Okay. An example of a critical point that does not yield a relative maximum, then there's a hyperbolic paraboloid. Okay. F of xy, which could be your z, is equal to y squared minus x squared. Okay. Now, if this was a constant, what you have is a hyperbola, okay? If that's a constant, you have a parabola opening upward. But if this is a constant, you have a parabola opening downward in the other dimension, okay? So sure enough, that's what you have here. You do have a critical point right there, okay? Everything is going to 0 there. First derivative this way, first derivative that way, a partial this way and that way. Looks like a dead state, except this is a relative minimum that way, a relative maximum that way. So that would be a saddle point, 0, 0, 0, even though your first partial and second partials are equal to 0. Now, we should have verified that, but let's do it. Oh, man. What's your f sub x? Pretty easy. Negative 2x, and your f sub y is 2y, okay? And where is this 0? At x equals 0, and this is 0 at y is equal to 0. So it seems like 0, 0 should be, and that is our critical point, but you don't get either a max or a min there. And how you verify that kind of is go a little bit away from 0, say in the y direction, but leave x equals 0, and this is going positive. Go a little bit away from 0 in the x direction, leave y equals 0, that's going negative. So going up this way, down that way. So that is a saddle point. Oh, man. All right. At the point 0, 0, both they're doing it here. Both partial derivatives, f sub x and f sub y, are 0, and the function does not, however, have a relative extremum at that point. In an open disk centered at 0, 0, the function takes on negative values along the x direction, positive values along the y direction, not going to be a extreme value overall at all. So the point 0, 0, 0 is a saddle point of that surface. Now, here's at least a first stab at how you can quantify that. Try to anyway. Okay? We'll have f having a continuous second partial derivatives on an open interval, okay, containing a point AB, for which f of x of AB, f sub x of AB, the partial of f with respect to x of AB, and the partial of f with respect to y AB are both 0. Our very points that we're looking at. Okay? So, it is a critical point. To test for relative extrema of F, consider the quantity. They call this, I'm pretty sure, at least some books do, a determinant. Okay? I'm going to say a lot of books do. Now, back in quadratic formula days, if you remember back that far, your minus b plus or minus the square root of b squared minus 4ac, that was called the determinant because that determined what was going to go on, whether you have one solution, two solutions, no solution, complex solutions, whatever. Well, here's your determinant here. They name it D. Okay? Now remember, you have to have continuous second partial derivatives here. So you take the second partial with respect to x at that point, the second partial with respect to y at that point, the product of those two minus the cross, I guess is one way to say it, your mixed partial, that's the way they use it, the mixed partial, L sub x, y, and if you recall, that's the same as alpha yx if everything is a nice continuous function. So it doesn't matter which order you do it, but do that in the square. Okay? That's what you determine. Your determinant. If this d is positive, meaning this value is larger than that value, okay? Obviously, these two would have to have the same sign, and they'd have to have values that were greater than that one squared. Because this is always positive, okay? Always positive. So these would have to have the same sign, and the product being greater than the square of that. So that's d being positive. And F sub xx positive also. So that means that F sub yy has to be positive. They don't say that, but it does. Okay? Then F has a relative minimum at AB. So if D is greater than 0, meaning this quantity is greater than that quantity, and the f of xx, the second partial with respect to x, is also positive, then we have a relative minimum. Okay? If D is positive, this quantity greater than that quantity, and f sub xx is negative, that means that one has to be negative. So guess what? You're opening downward in both directions. So that's a relative maximum. Okay? See, this implies relative minimum in both directions because that is positive and that this implies this one has to be negative as well. Okay? So that's a relative maximum. However, if D is negative, meaning that is greater than this product here is greater than that, okay? Then AB, f of AB is a saddle point. So if D is negative, if it ever comes up negative, that that this value is greater than that value, okay? Now, what if D were equal to 0? You don't know. Okay? Doesn't mean that it's not one of these other things, but you just can't get them from this text. So, quite often when you're doing these things, there are circumstances when you just don't know. Okay? And this is one of them. Okay. Now, interesting that, well, let's see, they may show these. No, they don't. Okay? They do show this too. If you think of that determinant, is what they call it, as a determinant in your, excuse me, linear algebra sense, the determinant of f of xx, f sub xy, f sub y, or xy, it doesn't matter which you do it, f sub yy, okay, because those two are the same. If you think of it this way, okay, then down, this is this is that minus that, okay? We did determinants in the other class, wasn't it? Yeah, it wasn't in this class. So it's also a determinant in this sense, you know, and if this thing winds up being positive, then you're a relative, well, positive, and either of these two are positive, then you've got to, that's a relative minimum. If it's the determinant is positive, but both of those are negative, then it's a relative maximum. And if that determinant is negative, it's a saddle point. But you have now, for that determinant to be zero, that in linear algebra, that implies you have a I want to say ill-posed system. That's not quite the right word for it. You don't have linear situations there. I'll just put it that way. But you don't need to know that here. Okay. But L sub xx and L sub yy, like I said, are the same. I'm sorry. L sub xy and L sub yx are the same. That was from back at Theorem 13.3. Long time ago in this chapter. Now we're ready for find the relative extrema of this function. Now this isn't one of our quadric surfaces, so you can't tell much just by looking at its form. So what are you going to do? What's your procedure? Partial of f with respect to x will be plus 4y. That's it. Okay? What you want to do next?
The second one,
F sub xx. Okay?
that is -6.
Got it. Okay? What you want to do next?
Partial of y.
Partial with respect to y.
4x minus 4y.
Okay, good deal. What you want to do next?
Partial of y.
Okay. Second partial with respect to y.
-4.
-4. What you want to do next?
Let's see.
Got at least one more to do.
xy.
Okay. L sub xy. And what would that be? You're going to do this one first, take that with respect to y, and you get 4. Let's do it the other way. Partial f with respect to y, take that with respect to x, and you get 4. Yeah, that just makes you feel warm and fuzzy, doesn't it?
Sure.
Okay. Now, what do you do with all that?
You multiply.
Okay.
The,
Actually, before you start testing, let's figure out, do we have any extrema? How do we do this?
set equal to 0.
Set that equal to 0. Now, where is that equal to 0?
That's 0.
Okay, 0, 0 certainly would be. Basically, where y is equal to minus 3/4 x squared. What does that define?
What does it?
What does that describe? Y is equal to minus 3/4 x squared. A parabola. That's exactly a parabola. Everywhere on that parabola, f sub x will be 0, right? Well, you set it equal to 0, and then solve for y. Oh, I got my sign wrong, didn't I? Plus, right? Because move the 3x squared to the other side and then divide by 4. Yeah. Okay, everywhere on that parabola, including 0, 0, your f sub x is 0. Okay, how about f sub y?
Well, every number.
Really?
Oh, wait, I'm sorry. Yeah. As long as x and y are equal.
That's it.
Yeah.
Everywhere, yeah, for every
That's what I
value.
meant to say.
Okay, I understand what you meant now. Okay. Where x equal y. Okay. So, if you wanted to, on your xy grid here, pretty ugly grid, but nevertheless, okay, let's plot a few of those parabolae. Okay, this one. You already said 0, 0. We got that.
3/4.
1 3/4, right? Okay, somewhere right about there maybe. And negative 1 3/4, right? Okay.
One and a half.
Okay. How about let's go on x equal. Okay. Second. How about, I think you just said it.
At 3.
At y is equal to 3 when x equal 2, right? X equals 2, y is equal to 3. So right there and right there. Okay. So this is going to be something that looks like this. Now, don't trust my drawing. Okay.
It's not that bad.
Okay. Now, y is equal to x is going to be something like that. 0, 0, you already identified. There is another point up here. Now, how you can tell exactly is that y equal x. So you have x equal 3/4 x squared. In other words, x 3/4 x squared minus x equals 0. And what can you do with that? It's your F word. Factor it. Factor out x. We know what that's going to produce. What do you have left? 3/4 x minus 1 equals 0. We know x equals 0. Yeah, we got that one. Okay, we had that one from the beginning. The second one is 3/4 x is equal to 1, meaning x is equal to 4/3. So this would be, my drawing isn't very good, something about right there. Okay, so 4/3 and what's the y value? Yeah, 4/3, right?
Yeah.
Okay, 4/3. Mine obviously isn't drawn very well. That would be down here somewhere. So that should be like this. Okay. I'll try not to get too close to the curve. So anyway, so there it is, right there. So there's our two candidates. Okay. 0, 0, and 4/3. Right? All right. These are the C values. I'll call it C1 is equal to 0, 0, and C2 is equal to 4/3. Okay. Now let's do our F sub XX. What were you going to say? You were trying to lead me down this path earlier.
Oh, you multiply sub XX minus sub YY. You subtract,
Wasn't there some value in front of that or not? I don't think so. Where have I? Yeah, just minus that, yeah. minus L sub xy squared. That's your determinant. Yeah. Now, let's plug and chug. Let's first do it for 0, 0. L sub xx would be 0, right? L sub yy would be times a minus 4 and minus 16. What does that tell you? That's a saddle point. So 0, 0 is a saddle point. Okay? Because your determinant is negative. Okay? Now let's go to your value. Yeah. We're trying to. Okay. I didn't ever identify this as at 0, 0. Okay. All right, let's do it at 4/3, 4/3. Okay? And your L sub xx there is negative 8 times negative 4 minus, I'm sorry, I put an equal sign, I'm going to put a minus sign. Oh, my eraser didn't pick up. Okay, minus 16. What does that get you?
16.
16. And we really don't care what it gives you except for the sign of it. What does the sign tell you? Okay. It means it's
Is that relative max at the point?
okay.
If B is greater than 0,
Okay.
it's
It could either be a max or a min. So it's the second tier that you look at.
okay. It's less than 0, so it's got to be the other way.
What's that?
It's got to be a min because
Sub XX.
the XX is greater than 0.
L sub xx is greater than 0.
Less. Is this negative?
That was negative.
Also relative max.
L sub xx was minus 6 times 4/3. That was a minus 8. So that's less than 0. Right?
I can't read.
Huh?
I said I can't read, man.
Yeah.
Yes.
Yeah. You didn't hear.
Less than
One was minus 8, one was minus 4. For this to be greater than 0, they have to be the same sign. Okay? And they're both negative. So they're both negative, opening downward in both directions that way. So this has to be a relative. Right. Good. Got it or not? Okay. Now, what we didn't do was find out what the z value was. Because when we're talking about these points, you need 3 coordinates because it's a 3-dimensional space. So at 0, 0, what was your F value, which is your z? 0, 0, 1. Okay? And that was a saddle point, right? Okay? And what's your second point? What's your point? Okay? I know it was 4/3. 4/3. It's going to be a little harder to figure, isn't it? Yeah. Okay. Minus 64/27. Is that right? I believe that's right.
Sure, yeah.
Okay. Plus 64/9 minus 32/9 plus 1. Hey, what are you with a calculator? Get to doing this. I'm not going to do this in my head. Okay? We could. It's not that bad. do it on paper, not in my head. We can do it. This is minus 64/27 plus 64/9 minus 32/9 plus 27/27. Okay. And this would be 3 times that, 192. And this would be 96. Boy. Minus 96 plus minus 64 would be minus 160. And minus 192, plus 192 plus 27 is, go ahead, the brain's not working. 219. So 219 minus 170, I think I said. I can't even do that in my head. 219 minus 170 is 49. Is that right? 49/27. I think I almost hope I made a mistake there.
It's 59/27.
69/27. 59, I missed it. 59/27, which is still a nasty number. Don't tell me they didn't even do it.
They did not.
They did not.
So I could just tell you the answer right off.
Oh, man. But one of the reasons I was doing that, hoping it would come out a nicer number than that one's at 1, this one's at 59/27, right? Well, this would be hardly any way for this to be a minimum, because it's greater than that one. So it would have to be coming up from there. So yeah, this is the maximum. It's considerably more than 1. Greater than 2 in fact. So at 0, 0, you have a saddle point down there at 1. And then here, further up here, you have a relative maximum. Okay. An incredibly weird looking shape. Okay. But they did a good job drawing it. All right, for me to erase my chicken scratch. You're saying please? Okay, I got it. Okay. Now, let's see how they did it. Begin by finding the critical points. How you find the critical points? Take your partials. Okay, partial of the first was that, just like you did. Partial of the second was that. We didn't do them in this order, but that's fine. They exist for all x's and all y's everywhere. The only they exist for all x and y. The only critical points are those for which both the first partials are equal to 0. Okay? So this is going to be a parabola. Y is equal to 3/4 x squared. This is going to be the line y is equal to x. Okay? To locate these points, we set each of those equal to 0. Add. You know that y is equal to x is the second equation while they did this. Then substitute it back in the first equation. They didn't do the parabola part, and they got x equal y equal 3/4. I guess that actually was easier than the way we did it. But I sort of wanted you to see zeros are on here, zeros on here. Those are going to be the places where they are. both of them equal 0.
Your
This
your
is
way made more sense.
well, yeah, this is just sort of blah, 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 but here it is. Okay.
It's like how they get 4 thirds.
Yeah. Well, they had x equal y here and then plugged it in here, like this x. So, yeah, they wound up doing the same thing. I mean, almost came out exactly the same. I mean, certainly the same values. Okay. Now we go back and do the second partials, which they hadn't shown us, but here they were. Second partial of that was minus 6x. Second partial of that with respect to y was minus 4. And that's what we got there. And then this partial of f with respect to, second partial of f with respect to y, first x and then y, oops, I'm turning the wrong direction, was, whoops, x and then y is plus 4. Sorry, my nose is itching like crazy. And second partial of y with respect to x would be plus 4. So they both work out that way. Oops. Plus 4, yeah. Now, it follows that for the critical point 0, 0. You do each critical point separately now. 0, 0, and 4 thirds, 4. No, I've already forgotten. 4 thirds, 4 thirds. Yeah, 4 thirds, 4 thirds. Do it first here. You get negative 16 for your determinant. I mean, it has to be a saddle point. No question about it. Has to be, and they plugged in and found out that's going to be a 1. So they did the easy one. Shame on them. Shame. Okay. Furthermore, for the critical point 4 thirds, 4 thirds, you do the same thing we did, and that's going to be a lot, not a lot messier. But the second partial of f with respect to x was minus 8. Second partial of f with respect to y both times was minus 4. And that one, remember, was 4, so minus 4 squared is 16. That gives you 32 minus 16 is 32. I mean, it's 16 to it. All right. Now, so your discriminant there is positive, but then just looking right here, you see this is negative, that is negative. You don't need both, you just need one. They just said the first one. But, yeah, they're both going to be the same sign if you've gotten this far in the test. Okay? And that's, so the discriminant positive and either one of the other negative, both of the others being negative, you know it has to be a relative max. It's greater than 0. That's all they say. Okay. Because that you can conclude that alpha is a relative maximum. Isn't this pathetic? As a maximum at 4 thirds, 4 thirds. They don't say what it is, whereas over here they made 0, 0, 1. They said what that one was. That's plumb sorriness. Okay. And sure enough, it is something greater than 2. I don't know if you can tell by this, but it is slightly greater than 2. And because that is, then that would almost tell you it had to be a relative maximum with a positive determinant. Okay. Far better rendition of the graphic than I would ever have done. Any questions on that? All right. Now, are any of these absolute? Either of them absolute? No, absolutely not. Okay, because this has lots of points below that one. Well, I mean that's a saddle point anyway. It has points on either side of it. Look, lesser here, greater there. So that could be. This is a relative maximum, but look at here. Lots of points over there. Way more. Okay. So absolute extrema. Absolute extrema of a function can occur in 2 ways. First, some relative extremum may also happen to be an absolute extremum. Okay? Neither one of ours were before. Okay? In fact, only one of them is an extremum. For instance, example 1, I think that was one we did last time. Absolute, yeah, that was a circular paraboloid or something like that. So yeah, it was absolute minimum of the function. On the other hand, the relative maximum found in example 3, not an absolute maximum of the function. Okay? I don't remember example 3. Oh, that's the one we just did. Yeah, that one that we just did. That was. Secondly, the absolute extrema can occur at a boundary point of the domain. Okay? Now that's if it has a closed domain. Okay. Oh, that's all they say about it. Yuck. Okay? I was expecting something a little more following from that, but no, that's all. All right, so what we've got to do, we still got to do example 4 and 5. All right, so let's do example 4 here. Oh, man. Find the relative extrema of this function. F of xy is equal to x squared y squared. Okay? What would be your first step? With respect to x would be y squared. Perfect. What you want to do next? F sub xx would be 2y squared. What you want to do next? F sub y is equal to 2x squared y. Let me, yuck. Oh, man. I'll leave it alone. Okay. What do you want next? Okay, with respect to y? 2x squared. And what next? Okay. What are you doing partial? Can we go and do the other one?
Sure.
What is it?
XY.
And what would that be? 4xy. Let's do it the other way. Second partial F with respect yx. That would be
2x.
not 4xy again. Yeah. Right? Yeah. Okay. It better be. The only reason I have you do it is make sure that we did it right, and we did. Okay. Now, go back to what you were saying.
Yeah, proof points. 0, 0, 1.
Okay, 0, 0 certainly is 1. As it would be here. Now, anything else you can say? Anywhere where x is equal to 0, or anywhere where y is equal to 0. So everything along the y-axis, everything along the x-axis. You also have critical points there.
What about 1?
Huh?
At 1, 1.
Yeah.
Oh, wait, it's not equal to 0, though. I'm sorry.
Yeah. So anywhere x is 0, both of these are 0. Anywhere y is 0, both of them are 0. So, but that's still only 1 point, isn't it? 0, 0. Well, They're both zero at any. Yeah.
I'm trying to see why would you pick one? What was you trying to do?
I don't know.
It worked last time. No, I'm sorry.
I really don't know.
Yeah. So,
Do you have
but-
a choice? Can you pick what you want to pick just to check and see?
yeah. If you put x equal 1 and y is equal 0, it works. You know,
As long as one of them is zero.
either one of them is 0. Right. You got critical points all along both axes, which is a lot of critical points. Okay. Now, what's the next thing we do?
Multiply the,
Let's use the origin,
okay.
because we know that one.
Well, it'd be 0 minus.
Yeah, minus.
0.
And what's true when the determinant is 0? You don't know beans. Okay?
Better use a different method.
Yeah, well, there's just no way of telling. Okay, now, let's think about what's happening here. If we can visualize what this looks like here. Along the line y is equal to x, okay, then this thing is going up steeply, isn't it? So 1, 1, 2, 2, 4, 4, you know, whatever. Is it any steeper than any other places? Seems like it would have to be. But anyway, it's positive everywhere, except on the y-axis and on the x-axis, and of course in the origin too. Zero's there always. And nowhere else is it 0, but positive everywhere else, the function is. So that's why I said to me, it seems like to me at those points it has to be maxing out there because it's coming back down to 0 there. So it's, if you look in the book, not a bad rendition of it, okay? And it looks like to me that you'd have to conclude from that at least 0, 0 has to be a minimum. As are everything on the x and y axis, because everything else is positive everywhere. So it's leaving either axis, it's going up everywhere except the origin and of course both axes. So I think you'd have to conclude that's a relative minimum, absolute minimum all along those axes, okay? But the second partial test doesn't tell you that, okay? But thinking through it, you should be able to see that, okay? But, so second partial test won't answer your question for you always, even when it's obvious, okay? So let's move on to example 5. And this was talking about our extrema occurring in 2 ways, so I assume we're going to run into that on this one. Goodness, just show me a bed. Find the absolute extrema of this function. F of xy is equal to sine of xy. When have you ever had a function like this? I don't know. Okay. But let's do it. Oh, on a closed region given by 0 less than or equal to x less than or equal to pi, and 0 less than or equal to y less than or equal to 1. Okay, that narrows it down a bit. Oh, but now that we've got a boundary here, and it's a closed boundary, then we got to evaluate all our points on that one because they're asking for absolute extrema. Okay, so where do we begin?
The partials.
Okay, which one you want to do first? Okay.
We have negative y.
Okay.
Wait, it's not negative.
No, that's fine. If you want to do it that way, it's fine. Yeah, go on. It's not all of it, though. Cosine xy. Okay, that's very legitimate. What you want to do next?
I don't think it's negative.
Oh, you're right. I'm sorry. Okay. I was thinking you were worried about the thing. Okay. Let's just get rid of that altogether. That equal sign is ugly, too. Okay. Yeah, you got it.
Then the second.
Okay.
Be y. Negative y squared. Sine xy.
Got it.
And the partial with respect to y. X cosine xy.
Y. Okay, never mind.
Negative x squared sine xy.
Okay.
xy.
Okay, this is a what?
We gotta do a product.
Product rule, exactly. So what would that be?
What? Minus y cosine cosine xy.
Okay. A little slower for me. I'm kind of dense today. I got the minus. I didn't get what you said after that.
Minus y.
Minus y. Okay, I'll buy that. Sine of xy. Oh, wait, okay. Don't we have a square there? Well, I take it you were doing...
Doing x part first up there.
Yeah, you're doing this one, right? Okay, so you did the first, right, y, times the derivative of the second, which is minus sine xy. The chain rule, you're doing this with respect to y. Oh, that was an x there, isn't it? Not a y. I'm sorry. Did I not do it? Yeah, I think I did it right. That's xy.
Oh, it is.
Right? Because you then do the partial of this with respect to y. That would be x. Right? Okay. Now let's just do the other one to see. If we did the partial of this with respect to x, oh yeah, you got to do the other side. Yeah. Let's continue.
This is just plus, well, x. Cosine xy.
Done.
That's it.
That's it. Okay. Now, let's do the partial of this one, just to make sure this is with respect to x. Okay? So if you leave that alone at first, we'll give you minus y sine xy, yeah. And then you have plus cosine xy. Perfect. Okay, so that did work. All right, now, all that is for future, not for now. What do we got to do next? You said it, I think, earlier.
Earn the critical point.
Okay. And that you set this equal to 0. Okay. So that certainly is going to be true anytime y is equal to 0, right? So anytime y is equal to 0. Also true anytime
Cosine of pi halves, perhaps,
say again? Pi, okay. If you have xy equal pi halves, right? Okay. Now, xy equal pi halves is only going to be true at x equal pi and y is equal to 1/2. Is that the only place? Well, let's phrase it this way. At y is equal to 1 pi halves over x, pi over 2x. Is that right? That's an ugly pi, isn't it?
Yes.
Hey. Okay.
Y can't be above 1, so it can't be.
And so we also know that 2x is greater than pi. Is that right? Because when pi is equal to 2x, that would give you a 1. So the x has to be greater than pi halves. Okay, so this is a mess, isn't it? Okay, so there's a bunch of x's, anything between pi halves and pi, where that'll be the case. Okay. Now, is that all? I think so. Okay. Now, this is that or that. Well, let's say y is equal to 0 or x greater than pi halves. Wait. X greater than pi halves and y with y equal to this. Yeah. Okay. We'll come back to that. All right. That's a mess. We'll come back and mess with that. Now, set this equal to 0, and where's that true? Okay, that would either be x equals 0 or xy equal to pi halves, which then everything's going to be the same there. So that's going to be true at, let's just take, for instance, pi halves 1, and then let's just pick another one. Pi 1/2, and everything in between, right? I think that'll work. Okay. Okay.
why would, if we go all the way around to pi, minus 1, oh, it has to be greater than 0. Okay.
Yeah. So xy equal pi halves, that's a hyperbola. It was true for both of these. So let's do this on the xy plane. So x is going from so this will be pi halves pi. Y is going 1, 2, 3. Oh, but it's staying with 1. Okay, right. And minus 1. Well, no, it's not even going down there. Okay, forget that. And x's are going over here. I should have stayed in the first quadrant. Okay, now let's list a few of those.
So pi over 2 is going to be y, that's 1/2.
Yeah, that would be the one point we know would be pi halves 1, and the other one we know is pi 1/2. Okay, now that's going to define, that's part of a hyperbola. And that's not completely obvious why that's true. But x can't be something, just say 1/4, because yeah. Okay. So I think that's it, that little strip there. But everything on that strip. And they name it a hyperbola. I'm not certain. Yeah, it would have to be, because xy equal that.
And it's 0, 0.
And 0, 0 was the other one, right?
0.
Yeah. Okay.
That's a weird.
Yeah. So those are the places where there are critical points. Okay. Now what we have to do is figure out, let's do our thing for 0, 0. F of x at 0, 0 is going to be 0, right? And f sub y at 0, 0 is going to be 0. So our determinant is going to be 0 minus, and what's your f of xy at 0, 0? Which is 1. So that's going to be a...
I just haven't memorized them. I haven't done that.
Yeah. Anytime that determinant 0 is saddle point.
Saddle point.
Yeah. So at 0, you got a saddle point. Okay? 0, 0, you got a saddle point. Now this picture, I don't see it very well here. They say an absolute minimum. Well, I guess, yeah, because it cuts off there. This is on the boundary there. If you came over here, it would be a saddle point. But you're not. You're stuck in here. So it's coming down here and here. So at 0, 0, this is 0. Now anything beyond, when x is 0 to pi, this thing is increasing. Y stays between 0 and 1, so this never exceeds pi. So this thing is always, sign is always going up in every direction from here. So this has to be where x equals 0, which is here. So all along here, you have this function is 0. See that?
Oh, and I see it now in the drawing.
Yeah.
You said
Because anywhere x is 0 and anywhere y is 0, this is going to be. So you're 0 here and here. Okay. Never goes below it. It would if you allowed it to, but it wouldn't. It would be a saddle point if you but see, the boundary condition you can't apply. That only works for things on the interior. So that's going to be everywhere else. This thing is positive in this range. Our domain here is just that. Okay. So everywhere here at 0, everywhere here at 0, everywhere else is going up. Now, what we don't know is what's happening here. Okay? That's where xy is equal to pi halves. Right? That's what this thing is describing. Xy is equal to pi halves. But xy equal to pi halves, that's 1. And that's the greatest step it can ever be. So that's an absolute minimum along this thing, absolute maximum along this thing, absolute minimum along that thing. You now have no interior points that would use your test. So all this was in vain. Okay? The xx, yy, and xy. None of those are going to be meaningful here because you're dealing strictly with your whatever you call it, your boundary values. Okay. Here, your minima, and all along here, your maximum. Equal 1. Oh, wait. We forgot something else, too. It's defined everywhere here, including out here. So we have to check really all of our boundary values. Okay? Not just these two, but here. Now, where y is equal to 1, okay, let's go up to x equal pi. X equal pi, where y is equal to 0, that's going to be 0, of course. We already said that's a minimum there. Okay? It's going to be increasing until it reaches the max right here. Okay? Because it can't get any greater than 1. What happens when y exceeds that, though? And x is at pi, and y is something greater than 1, or greater than 1/2. Greater than 1/2. Now it's going downhill, because the sign is going like this. What does it reach when it gets here? And xy is equal to pi. Xy is equal to pi, which you can't get to. 1 here, pi here. What is sine of pi? 0 again. So there's another minimum. I almost forgot about that one. So that's the minimum. You have to consider all so you're up here at 1 here, and you're at 1 here, and you're 1 all along there. Down here, you're heading downhill to 0, and over here, you're heading downhill to 0. And along that curve, you're at 1. So anywhere here, the x is between 0 and pi, so y is equal to 1, you're going downhill, sinusoidal curve. Here you're going downhill, sinusoidal curve. Everywhere you're going downhill, reaching 0 there and 0 here. Weird looking thing. And like I said, when will you ever have anything that would look anything like that? But that's what they have. So the absolute maximum is along this thing, xy is equal to pi halves, absolute maximum. Absolute minimum are along these two boundaries here and that single point over there. Bizarre, okay? mathematicians, math book authors find these weird things to drive you nuts. Okay. Homework exercises would include any of the odds 3 through 7. They're all at Calc Chat. 7's at Calc View. Any of the odds 9 through 21. How about 9 through 19? They're all at Calc Chat. 9's at Calc View. Then do either 21 or 23. They have pictures of those, so do one of those two, at least one of those two. They should be at Calc View. Either 25 or 27, they should be, at Calc Chat. 25 or 27 should be at Calc Chat. 29 should be at Calc Chat. You can think about doing 31 or 33, sort of interesting to look at. Then either 35 or 37, all those should be at Calc Chat. Any of the odds 39 to 45, they're all at Calc Chat. 39's at Calc View. Man, I can't breathe. Do 47, it's a Calc Chat. You can export doing 49 and 51. They're both should be at Calc Chat. 53 should be at Calc Chat. There's a couple true false. 55 and 57 should be at Calc Chat. And that's it. All right. Now, I think what I said before, we'll just do a slideshow of the next two sections. No, you're not going to be tested on this. We just don't have time. They're not that long as sections, but it would take a while to proceed. So, how are we doing time-wise? I'm completely lost. Yeah, a few minutes. So let's get as much of the slideshow done as we can. I'm sorry, my brain's not working well today. And what did I just do? I don't know. Oh, wait, I don't need to do that. I already had it open. Well, I have to do it now. Okay. 13:9. All right, slideshow. Oh, man. Okay. Still functions of several variables. 13.9 is applications of extrema. Solve optimization problems using functions of several variables and use the method of least squares. At least we'll show you the method of least squares. So applied optimization problems. Here's what we got. The rectangular box is resting on the XY plane. There it is, sitting on the XY plane. With one vertex at the origin. There, that right there. Okay? The opposite vertex lies in the plane. 6x plus 4y plus 3z is equal to 24. Now, how do you find the intersections of those? Well, set these two equals 0. Y and z equals 0, and then you're on your x only, so that would be x equals 4. So 4, 0, 0 is right there. Do the same thing here, and 0, 6, 0 is 24. There that one is. You do this here, and you get 0, 0, 8 is 24. So that gives you the three vertices of this triangle, and this plane goes like that. Okay. So the opposite vertex with this one lies on the plane. Now, you could squish this down some and let this crawl down the plane this way, or you could stretch it up this way and let it crawl up the plane this way. Okay? Those are various things you can do. Now it's a rectangular box, so you could have it fatter in the x direction or in the y direction, and do whatever it takes there. Okay. Find the maximum volume of the box. Okay? Well, you'd have to determine what the volume of the box is. The volume of the box would be your x times your y times your z. Okay? So v of the box is x times y times z. Okay? Given these constraints on it, okay? And that's given you're constrained by this plane. Okay, so let x, y, and z represent length, width, and height of the box. Because one vertex of the box lies in the plane there, you know that z is equal to.
Okay, they just moved it.
Oh yeah, you solved for z, right? Okay, yeah, that's all they did. So you can write the volume of the box as y z, but instead of z, you use this for your z. So now you have the volume of the function of x and y alone, because this has x, that has x, those have x, y's, x's and y's. So now you can take the partials of this and find the maximum. I'll tell you what the minimum are. When the plane is flat, I mean when the box is flat, or when the box is here, or when the box is there. Those are going to be the minimum. So if you have a maximum, my gut feeling is it's only going to be one. Okay? So what we're going to do, multiply this through 1/3 x 24xy. So that'd be 8xy minus 2x squared y minus 4/3 xy squared. Why they write it this
You
way?
only need to know that we're only finding that one point, and then we know all the others, right?
You
Like
mean,
that one point that touches.
yeah, well, yeah. On that one point, the volume is x, y, z for that one point. Yeah.
Once we know it, we know all the others.
Yeah, because they all fit this criteria. Yeah, yeah. All right. So you do your partials. Now, why they hang on to the 1/3 there, I'm not sure. But they're doing it, so we'll do it too. So this will be partial. I wasn't going to do these, but they do them on different planes here, different slides. And they'll wind up with this. You do the partial with respect to y here, and you wind up with this. Okay? Okay? Note that the first partial derivatives are defined for all x's and y's, all. So by setting v sub x, v sub y equal to 0 and solving the equation, so that's what we're going to do to get where they're in common. Each of those equals 0. You obtain the critical points. So it's pretty obvious. Y is equal 0 is going to make this 0. X equals 0 make that 0. So 0, 0 is certainly going to be 1. Guess what? At 0, 0, 0, your volume is 0. So we'll basically throw that one out. That's not going to give you a max. It's a critical point. Okay? Now, where else? Where this is equal to 0, we took care of this one, so y is equal to 0. Where this is equal to 0, that would be, let's first do a 0 here, and that's basically what they'll do is 0 here first, and that would be x equal. Oh, wait, yeah, okay. So this to be 0, 12x minus 4y is equal to 24. 12x plus 4y is equal to 24. Divide everything by 4 and you get 3x plus y is equal to 6, okay? And then do the same thing here and pick the points in common. So that's how they came up with these other values here. Okay, well, I'll tell you this. If y is equal to 0, like I said, if y is equal to 0, you got a zeroed value. If x is equal to 0, you got a zeroed value. And if z is equal to 0, you got a zeroed value. So those are all minimum. Okay? Okay. So basically, there's your max. Now that's perhaps not doing it mathematically, but that's doing it practically. Okay.
Then just plug that back in.
Yeah, so these points do not yield maximum values. At that point, you can apply the second partials test. Okay. And I guess they're doing it in pieces here. I was going to say they did it all at once. Okay. Your discriminant 64 thirds, which is positive. Your VXX, which you did right there, plug in this would be a -8. See it right there. So this has to be a maximum, which we knew already. The other are minimum, these are max. Okay? You can conclude the second partial test that the maximum volume is there, and then, like you were saying, plug it in, plug it in. 1/3 of 24 times 4/3 of 2 is, it looks messy, but it's probably not too bad. That's still bad. Okay. 3 will go to the 24 8 times. I'll take this 3 into it 8 times. And that's 8/3 times 8, 64 thirds. And you can do the math.
It equals 64 over 3.
Over 9? That's what they said,
Yes.
64 ninths cubic units. Okay. All right, note that the volume equals 0 at the boundary points of the triangular domain. Yeah. Ooh.
Looks like they made that a lot harder.
Yeah, I mean, they went through a lot of stuff to show you. Yeah.
Length times width times height, right?
Yeah, but that's where you started. But you had to find out what that point was. Yeah. And that's what the partials do. But as soon as you got that the other
Once
three
you
are
know that
minimum,
point,
yeah, you're done. Just plug it in. Now let's talk about the minimum method of least squares. Many examples involved. Oh, are we at? Whoa! Look at what you let me do.
oh, we're getting,
Huh?
you're losing pay here.
Yeah. All right. We'll pick up the slideshow at method of least squares. We're not going to do the method of least squares. We'll just show you how to do it. You don't have any additional homework here. And by the way, there is a, well, I'll talk about that next time. All right. Let me end this. Yeah, we went, still didn't do an hour 40 though. We did an hour 30.